Hello everyone, I'm Dr. Koushik Mondal. I'm from Holdia Institute of Technology, and today I'm going to talk about the interference of light. In the first lecture, I'll talk about the first part of the interference of light. So basically, the first part of the lecture, I want to talk about the syllabus of this interference that is included to our MacOut syllabus. First, I want to describe the definition of the interference. I mean, what is interference of light? Then I will talk about the classification or types of interference, just like that interference by division of wavefront, interference due to the division of amplitude. These two are two distinct type of interference of light. And then I will talk about the Newton's ring experiment. I mean, what is the aim of this experiment and how to determine the wavelength of an unknown source of light by using the Newton's ring experiment. And also using this experiment, you can calculate the refractive index of an unknown liquid. Okay. So in the first talk, I will talk about the interference due to the division of wavefront. And so first, I want to talk about some basics of the light. So what is light? First thing, the first question came to your mind. What is light? Light is nothing but the some form of the energy that a light wave transferring from one place to another place. And you can directly say that light is an electromagnetic wave whose wavelength lies in the visible range. That's mean that whatever we can see. I mean that is at the visible range, and the wavelength range is ranging from the 380 nanometer to 740 nanometer, and 1 nanometer is nothing but 1 to the power minus 9 meter. Okay, so the visible light are ranging from the violet to red. Violet has the lowest wavelength and the red has the largest wavelength. And this light is nothing but the photon, and it will follow the Bose-Einstein statistics. Okay, so in the next I will talk about some basics of the wave. What is light? Light is an electromagnetic wave. I have already told you. And here, what is wavelength? Wavelength is nothing but a wave is nothing but a distance that is covered in a wave shape, and wave shape is repeat itself after some distance. And if we consider a light wave can be described by a equation of y equals to xt. I mean, it has the both space modulation as well as time modulation. So yxt equals to a sine omega t plus kx, where omega is the angular frequency, and angular frequency is nothing but 2 pi n. N is the natural frequency. K is the wave vector. Wave vector is equals to 2 pi by lambda. Lambda is here wavelength, and A is the amplitude. That is the maximum displacement along the y-axis. Next, what is the phase difference and the path difference? Let us consider two waves. Here is the blue, you can see blue, and another is the pink. And the blue wave is described by a sine omega t, and the red one is, or pink one is the y equals to a sine omega t minus pi by 2. If you closely look at these two waves, you can find that at t equals to 0, the blue wave has nothing, no displacement. That means zero displacement. But the red one has some displacement, is minus of a. Right, so the red wave is something advanced to this blue line. So the difference in space difference between two waves is known as the path difference, and the angle of the phase angle difference. What is phase angle? Here you can if you look at the wave equation of a for the blue one, y equals to a sine omega t, it has no additional phase. But the red one has an additional phase of minus pi by 2 or pi by 2. So this phase difference between two wave is nothing but the difference of the phase angle, and it is pi by 2, and the path difference between two wave is lambda by 4. There is one to one correspondence between the phase difference and the path difference, and this equation is written as phase difference delta phi is nothing but 2 pi by lambda into the path difference. So this has a one to one correlation. Now, what is the principle of superposition? I mean, what these details I am telling about before going to the interference phenomena. This is very basic, and it is required to understand the phenomena interference of light. So, what is superposition? The statement is that the principle of superposition states that when two or more waves overlap in a space, and resulting disturbance is the sum of individual disturbance. For example, if you consider some wave is described by y1 equals to a1 sine omega t plus phi1. Here phi1 is the phase angle and y2 is a2 sine omega t plus phi2, and so on. If you consider here is n number of wave, and the superposition principle of superposition tells that the resultant disturbance y is nothing but the sum of individual waves. That's mean y equals to y1 plus y2 plus y3 and up to yn. And in compact form is sum over n an sine omega t plus phi n. So if we consider two, pictorially it is also shown here. If we consider two waves, or consider the blue and the green, two waves are bond is passing through the medium, and if we consider the time evolution or time advantage of this wave is depicted over here, and the superposition, after the superposition you can get the red line. Okay, so red line is the superposition of the blue and the green wave. Now, interference of light. First, Christian Huygens suggested one satisfactory explanation. Before that, there is a debate: light is a wave or particle? Corpuscular theory, if you know. But here, Christian Huygens first suggested one satisfactory explanation of interference and diffraction phenomena by assuming light as a wave. So, what is interference? Interference is the most general phenomena. You can also see the interference in the light wave, sound wave, even in the water wave. What is the statement? The modification of the intensity due to the superposition of two or more light beams is known as the interference of light. For example, if you have a two light source, point source A and B, and they are producing light waves, and after the interference, the resultant wave we have to find. So if we place one screen in front of the two source A and B at some distance, you can see that the light wave is traveling in the medium, and after the superposition, you can see some interference pattern over the screen. What is the interference pattern? In screen, you can on the screen you can see some spot of bright fringes and some part are the dark fringes. That means some spot are the dark spot and some are the bright spot. So this is due to the interference of light of coming from the source A and B. So we need to understand it more, and there is a class. I mean, you can classify the interference. There is a two type of interference. One is the division, I mean light interference. Interference due to the division of wavefront, and another is the interference due to the division of amplitude. Throughout this talk, I will talk about the interference of light due to the division of wavefront, and in the next lecture I will talk about the interference due to the division of amplitude. So what is the interference due to the division of wavefront? Here, if we consider some point source, like some point source, light is coming from some point shaped source, and after from which light waves spread out in the spherical or cylindrical wave, and any 2 point source on such a spherical or cylindrical wavefront are taken as the interfering sources, and after interfering, I mean light coming from these 2 point sources, you can get the interference due to wavefront coming from these 2 point source. And here is the example of Fresnel biprism, Lloyd's mirror, and the violet splits. What is the interference due to the division of amplitude? For example, if you have an extended source and the device which divide the amplitude of the incoming wave of light into two or more parts by partial reflection, refraction, and then if we consider these two as separate sources and if we allow them to interfere, then you can get some interference pattern on the screen. And some example of this thing is the Michelson interferometer, Newton's ring experiment, and Fabry-Perot interferometer. Okay, in the next lecture, I will talk about the Newton's ring experiment in details. Okay, what is wavefront? Before going to the more details about the interference due to the division and due to the division of wavefronts, I am talking about the wavefronts. So, what is the wavefront? According to the wave theory, a source of light sends out disturbance in all possible direction, all 3D direction. So, in a homogeneous medium, the points that are situated at the equal distance from the source of the light will vibrate in the same phase. Okay, and the locus of the all particular vibrating locus of all the particles vibrating in the same phase are phase phase at any time is called the wavefront of the wave produced by the vibration of the particles. For example, you throw one stone on the calm pond water. Okay, on the surface, if you find that after dipping this stone, you will find some ripples of the water wave around the point of contact. And if you find that the circular ripples spread out from the point of impact and each point on the circumference of the circle oscillate with the same amplitude and the same phase, thus we can get a circular wavefront. So you can classify the wavefronts in three categories. One is the spherical wavefront, another is the plane wavefront, and another is the cylindrical wavefront. To get the spherical wavefront, we need one point source, point-like source, light source. And you can find that this light will spread over in the 3D in 3D, the light will spread out from the point source, and you can consider one sphere on the every point on the sphere will have the same state of same phase, and the locus will be spherical, and this type of wavefront is the spherical wavefront. You can see in the figure A. Plane wavefront. What is the plane wavefront? If you consider, you can see the locus at a large distance from the source, a small portion of the sphere can be considered as a plane. I mean, the radius of the sphere is very large. If you consider the radius of this sphere is very large, then you can consider small portion of the sphere as a straight line. So this is the plane wavefront. You can see this in the figure B. What is the cylindrical wavefront? If you consider one cylinder-like source, for example, you can consider one tube light and light coming out from the line source, and in the cylindrical surface you can get all the point on the cylindrical surface in a same phase. So the wavefront coming from the line source are in cylindrical shape. So what is the first part is interference due to the division of wavefront. You can easily get one sense by the Young's double slit experiment. So what is the Young's double slit experiment? See the arrangement for the first figure. So S is a point source, light coming from the source S, and in front of the source you can put one sheet with two small pores, right? S1 and S2, small slit. Hmm. And light will pass through these two slits and interfere with each other. And if we put one screen on in the XY plane, we can have alternate dark and bright patches on the screen. So why it is happening? So we consider is point source is here. So it is point source is always spreading out one spherical wavefront, right? So after contacting this uh, this spreadsheet is where the slits S1 is S2 are residing. After that, after passing through these points, it will divided in two wavefronts, right? Both are cylindrical, spherical in shape, and on overlapping this wavefront coming out from two source S1 and S2, it will interfere, and you can observe the alternative dark and bright spot on the screen because of the overlap of the wavelength coming out from the source S1 and S2. So this is the very easily with observable, very handy experiment, Young's double slit experiment of interference due to the wavefront, division of wavefront. Next, we want to analytically study this phenomena. So how to handle this thing? For example, S1, S2, I have already told you that these are the point source, and light coming out from the source uh, are overlapping to each other, and we put one screen and want to calculate the intensity at the point P. So for that, to get into this matter in more general way, let us consider S1 and S2 two source of monochromatic light of wavelength lambda. Okay, let two light rays from S1 S2 proceed along S1 S1P and S2P path and superpose at a point P on the medium. Let's say it is some point on the screen. From the principle of superposition, we know that this resultant displacement at P at any instant is algebraic sum of the displacement P at P at any instant of time. Let us consider the waves have a analytical expression of y1 a1 sin y1 equals to a1 sin omega t and y2 equals to a2 sin omega t, and both here a1 and a2 are the amplitude of both the waves, and omega t is the angular frequency. The first one have no phase difference, but the second one has a phase difference of delta. Now you use the principle of superposition, and the resultant displacement at P is uh, is nothing but the algebraic sum of the waves y1 and y2. So resultant wave y equals to y1 plus y2 equals to the a sin omega t plus a2 sin omega t plus delta. So you prove a, we will expand this expression, second term of this equation, sin omega t plus delta in the sin a cos b plus sin a plus b formula we will use, and it is sin omega t cos delta plus cos omega t sin delta. And if we rearrange this equation in as a coefficient of sin omega t and cos omega t, we will find that a1 sin omega t, a1 plus a2 cos delta into sin omega t plus a2 sin delta into cos omega t. So we need to have a resultant wave in the form of individual waves. So here we consider the coefficient a1 plus a2 cos delta equals to a cos phi, and the a2 sin delta equals to a sin phi, capital A sin phi. So if we substitute this assumption in this equation, then resultant equation will come as y equals to capital of A cos omega t, sorry, sin omega t cos phi plus sin phi cos omega t. So it is nothing but the formula of sin A plus B. So resultant wave is equals to A sin omega t plus phi. So you know this, the intensity. Intensity is nothing but the square of the amplitude. Okay, so we need to calculate the A in terms of A1 and A2. So from this expression or assumption, we consider A1 plus A2 cos delta equals to A cos phi and A2 sin delta equals to A sin phi. So from here, if we square and these two equations both and add from the both side, then we can get a square equals to a1 square plus a2 square plus a1 a2 to a1 a2 cos of delta, and the phase angle is nothing but phi equals to tan inverse of a2 sin delta by a1 plus a2 cos delta. Now we already obtained this expression for the resultant amplitude. So we already told that the resultant intensity is nothing but the square of the amplitude. Okay. So resultant intensity I equals to a1 square plus a2 square plus 2a1 a2 cos of delta. So remember this expression. From this you can solve some problem related to the interference due to the division of wavefront. So next what will come? So we have already witnessed the there is a some bright spot and the dark spot on the screen due to the interference. So what is the condition? We need to get this thing. So first is the condition for the constructive interference. Why it is? So what is this? The constructive interference means that there is a resultant intensity is bright. So if we consider delta equals to 2n pi, okay, n is 0, 1 to natural number. So cos delta equals to 1. So if for this condition, the resultant intensity Imax equals to a1 square plus a2 square plus 2a1 a2 equals to a1 plus a2 whole square. So why this condition? We get this condition for delta phase difference equals to 2n pi. That means the even multiplier of pi. So from this, I already told you there's phase difference and the path difference as a connection. Phase difference is nothing but 2 pi by lambda in the path difference. So here path difference is S2P minus S1P, if you remember the picture. So this is nothing but for the 2n and the pi is corresponding to the lambda by 2. So for the all point on the screen, all the bright spot in on the screen is coming for the path difference of even multiplier of lambda by 2. The waves will interfere constructively, producing the light, the bright point, and the interference is known as the constructive interference. Okay, and the next is the for the dark point. So this is called, this is the destructive interference. So if you consider delta equals to 2n plus 1 lambda, that is the odd multiplier of pi, then you can get cos delta equals to minus 1. If you substitute this thing is the resultant intensity, you can get the minimum intensity I mean equals to a1 square minus plus a1 square minus, sorry, a1 minus a2 whole square. So the path difference S2P minus S1P is nothing but 2n plus 1 into lambda by 2. So all the points where the path difference is all the points on the screen where the path difference between the two source is odd multiplier of lambda by 2, then the waves will interfere destructively and producing dark point on the screen, and the interference is known as the destructive interference. So if we plot this result, the resultant intensity I in terms of the phase angle, then we can observe that when this delta or odd multiplier of pi, then you can have the lowest intensity, that is I mean equals to A1 minus A2 whole square. And when this I max will appear when the delta is even multiplier of pi, which is equivalent to the path difference of lambda by 2, or even multiplier of lambda by 2. So this is the distribution of intensity with the phase angle delta. Next, we will consider the conservation of energy. If we consider here the intensity is minimum, but here intensity is maximum. So does it conserve the energy? So if we calculate the average intensity, then you can have it is the I mean integration. Here is the ratio of intensity I delta by delta. Okay. So in this expression for I is a1 square plus a2 square plus 2a1 a2 cos delta into delta by 1 over delta. This lower integration is nothing but 2 pi, and the upper integration come as a1 a2 square plus 2 pi. So this individual and the cos sine delta is 0. Integration over sine delta is equals to 0. In one cycle, this integration will give you 0. So the integration average energy integration is nothing but the intensity of the individual sources. So what does it mean? This means that when that the energy of the maxima is increased at the expense of the energy of the minima. I mean, whatever the energy is reducing in the minimum position, it will actually transfer to the maximum intensity point. So that is why you can repeatedly periodically getting the lowest intensity point and the maximum intensity point. So there is no loss of energy. Energy is conserved. Okay. So next is the conditions for the sustainable or permanent interference. The interference pattern in which the position of maximum minima intensity of light remains fixed along the screen is called the sustained or the permanent interference pattern. So if the conditions to achieve this permanent or the sustained interference, we need the sources must be coherent. What does it mean? The phase angle between the waves must be constant throughout the space and throughout the time. Okay, and the source should be emit the light of the same wavelength and the nearly same amplitude. The source should narrow and close to each other to observe distinct fringes. And the maximum path difference for at the maxima, I mean maximum intensity point, the path difference between the waves should be even multiple of the lambda by 2, and the minima odd multiple of lambda by 2. And the two light wave must have the same state of polarization. What is polarization? Polarization is nothing but the electric field vector. Light is an electromagnetic wave, and it is consists of the electric field vector. So this is related to the electric field vector direction. Okay, this thing will tell you later. So this look at the second condition. Okay, the source should have emit light of the same wavelength. So is there? I mean, the interference is still happening with the different wavelength, but the interference pattern will be very irregular. That thing is depicted in the lowest figure. So this thing wave has a the red wave and the blue wave are interfering to get the resultant intensity pattern is written, I mean depicted over here. But see, this red wave has a shorter wavelength comparison to sorry, the red light has a larger wavelength in comparison to this blue wave. Okay, and they're interfering. But here, if you observe one irregular pattern of the resultant intensity pattern, because there is wavelength and there is a different phase difference and the path difference. For that, this irregularity in the phase difference and the path difference give you this irregular pattern of the intensities. Okay. So see this, I have already told you that maxima and the path difference. For the maxima, the path difference should be even multiplier of the lambda by 2, and the for the minima, this thing will be the odd multiplier lambda by 2. So here this thing, this red wave and the blue wave has the same phase. You look at this thing. Okay, same phase, same amplitude, almost same amplitude, same wavelength and all that thing. So resultant wavelength is you can see resultant intensities. But for this case, this red and the blue wave in the exactly opposite phase. Okay, phase angle is pi. In opposite phase means this phase angle is pi. So pi means it is a odd multiple of lambda by 2. So for that only you have a zero intensity. Okay, so now you can solve two problem, easy problem. The path difference between the two interfering rays at a point on the screen is 1/4 of the wavelength. Find out the ratio of intensity of this point to that at the center of to that at the center of the bright fringe. That means the maximum and the maximum intensity. That means we need to find out the ratio the intensity found at the point P and the maximum intensity. And the second problem is that two coherent sources are there and whose intensities ratio are 49 is to 1, producing interference pattern. These two sources are interfering, and find out the ratio of the maximum intensity and the minimum intensity. So we need to find out this maximum after interference. We need to calculate the ratio between the maximum intensity and the minimum intensity. So how to solve these two problems? See this next problem. So what is this? Solution 1. We know the resulting intensity is nothing but the a1 square plus a2 square plus 2a1 a2 cos delta. For simplicity, we took here a1 equals to a2 equals to a. So the resulting intensity now become 2a square plus 1 into 1 plus cos delta. So central maximum will occur at delta equals to 0. That is the even multiplier of the of pi, right? So maximum will be 4a square, and at the point where the path difference is lambda by 4, which is equivalent to the phase difference of pi by 2. At pi by 2 cos delta equals to 0. So this thing I equals to 2a square. From the above expression you can find I equals to 2a square. Now the ratio is nothing but I by Imax equals to 2a square plus 4a square equals to half, right? And the second problem, it is given that two interference source has intensity ratio of 49 by 1. So Imax and Imin दोनों का ratio, I mean the ratio of the Imin and Imax is nothing but the a1 minus a2 square by a1 plus a2 whole square, right? So you have given that I1 by I2 equals to 49 by 1 is nothing but a1 square by a2 square. So also a1 by a2 is 7 by 1, or a1 equals to 7a2. If we substitute this thing in the above expression, then you can find I mean by Imx equals to 7a2 minus a2 by 7a2 plus a2, yeah, whole square. See, this is nothing but 6a2 whole square by 8a2 whole square. This is nothing but 9 by 16. So this is all about this thing. So small problem will be there. You can solve using this formula. So for further query, you can write to this mail, and for your concentration, thank you. Thank you for